learn like a pro.
So, have you ever stared at a physics graph and it just looks like a jumble of random lines? Well, believe it or not, every single one of those lines tells a story. It's the visual tale of an object's journey. And today, we're going to learn exactly how to read it. Let's dive in. Okay, take a look at this. I know it might seem a little complicated at first glance, but I want you to think of it as a puzzle. It's just waiting for us to solve it. And I promise you, by the end of this, you'll be able to look at any line, any curve on a graph like this and know exactly what's going on. All right, first things first. Before we can decode the journey, we need to understand our dashboard. And yeah, I mean that literally. Think of this graph like the instrument panel in a car. We're going to break down the absolute fundamentals of a displacement time graph. So every displacement time graph has two main parts, right? You've got the vertical axis, the y-axis, and that tells you the displacement. Now that's just a fancy way of saying the object's distance and direction from where it started. Then you've got the horizontal x-axis, which is always time. And that special spot where they meet, right there at 0, 0, we call that the origin. It's our fixed starting line for the whole journey. Okay, we have to clear something up right away because it trips a lot of people up. The difference between distance and displacement. Think about it like this. Total distance is like the odometer in your car. It only ever goes up, right? It just adds up every single meter you've covered. But displacement, that's all about your net change in position. So if you walk 10 meters forward and then 10 meters right back to where you started, you've traveled a distance of 20 meters, but your displacement is 0. Why? Because you ended up exactly where you began. All right, you ready? We're about to get to the secret key, the thing that unlocks this entire puzzle. Seriously, if you only remember one thing from our time together, make it this. It's the single most important rule for reading these graphs. I call it the law of velocity. And that key is a concept called gradient. Now, don't let the words scare you. It sounds like some complicated math term, but all it really means is the steepness of the line. That's it. It just tells us how fast the displacement is changing over a certain amount of time. You probably remember it as rise over run. And here it is. This is the big aha moment. The gradient of a displacement time graph is the velocity. I'm not kidding. This isn't some metaphor. The steepness of that line is the exact mathematical equivalent of how fast that object is moving. Because what is velocity? It's the change in displacement divided by the change in time. That's literally the definition of gradient. So, this is how we get direction into our story. If you see a line sloping upwards, that's a positive gradient, and that means the object has a positive velocity. It's moving away from the origin. And what if the line slopes downwards? Well, you guessed it, that's a negative gradient, which means the object is moving back towards the origin. Simple as that. So let's lock this in. The steepness tells you the speed. The steeper the line, the faster the object is moving, a really high velocity. A gentler, more gradual slope, that's a slower velocity. And what about a perfectly flat horizontal line? Well, what's its steepness? It's 0, right? So the gradient is 0, which means the velocity is 0. The object isn't moving at all. It's at rest. Okay, so we've pretty much mastered straight lines. We know they mean constant velocity. But now it's time to level up. Let's see what happens when we introduce curves into the mix, which is the visual language of acceleration. So think about this for a second. What happens when something is speeding up or slowing down? Well, its velocity isn't constant anymore, is it? And if the velocity isn't constant, then the gradient on our graph can't be constant either. And what does that mean for our line? It means it can't be straight. And there's our answer. A curved line simply means the velocity is changing. It's that simple. Look at the one on the left. See how the curve gets steeper and steeper? That means the gradient is increasing, so the object is accelerating. Now look at the one on the right. The curve is getting flatter. The gradient is decreasing. The object is decelerating. It's slowing down. Think of this chart as your visual dictionary for motion, your go-to guide. It shows pretty much every possibility on a displacement time graph. That whole top row, that's for moving forwards, away from the origin. You've got at rest, then constant velocity, then accelerating, and finally decelerating. And the bottom row, it's the exact same set of motions, just in reverse, moving backwards towards the origin. That's what the negative gradient shows us. Okay, you've got the roles, you've got the dictionary. Now it's time for the final challenge. Let's put everything we've learned together and analyze a full, complex journey from the very beginning to the very end. And here it is, our entire 20-second journey. I know, it looks like a lot is going on, but trust me, we now have every single tool we need to decode this. We're just going to break down the story of its motion section by section.
All right, let's zoom in on the first 2 seconds. What do we see? A nice, straight, upward sloping line. We know what that means. Constant positive velocity. So let's calculate it. The displacement goes from 0 to 4 meters, and that happens over 2 seconds. So gradient, rise over run, is 4 meters divided by 2 seconds. That gives us a constant velocity of 2 meters per second moving away from the start.
Okay, what happens next? From 2 seconds to 6 seconds, look at that line. It's completely flat. We already know what that means, right? The gradient is 0, so the velocity is 0. Its position isn't changing at all. It's just holding steady at 4 meters from the start. The object has just stopped. It's taking a break.
Now, from 6 to 9 seconds, things start to get interesting again. We don't have a straight line anymore. We've got an upward curve that keeps getting steeper. What does that tell us? The gradient is increasing. So the object isn't just moving, it's accelerating away from the origin, going faster and faster.
All right, let's skip ahead a bit to the part from 11 to 13 seconds. Whoa, look at that. The object has completely turned around. We see a straight line, but this time it has a negative slope. That tells us it's moving at a constant velocity, but in the negative direction. It's heading back towards where it started. And to finish the story, let's look right at the 20-second mark. Where does the line end up? Right back on the horizontal axis. What does that mean? It means the displacement is 0. After that whole journey, going out, stopping, accelerating, coming back, the object has returned to its exact starting point. The journey is complete.
Okay, I know that was a lot to take in, so let's boil it all down into a quick, super practical reference guide. These are your key takeaways, the things you need to decode any motion graph you see. And here it is, your ultimate cheat sheet. Honestly, it all comes down to just 3 things. If you see a flat line, the object is at rest, 0 velocity. If you see a straight, sloped line, it's moving at a constant velocity. And if you see a curved line, you know its velocity is changing. It's either speeding up or slowing down.
But let's circle back and repeat the single most important rule one last time. The one thing I really want you to burn into your memory. The steepness of the graph, its gradient, is the exact mathematical equivalent of the object's velocity. Master that, and you've mastered these graphs.
So now, you don't have to look at these graphs and see just a bunch of lines on a page anymore. You can actually read the story, the dynamic unfolding story of an object's motion. You have the tools. So the only question left is, what story will the next graph tell you?